Good day. Welcome to the Engineering and Geosciences Annual Research Summit. I am Trisharia Menenza, a fifth-year mining engineering student under the advisory of Engineer Jerome Humper. To start, our research study is entitled Determining Suitable Location for Silt Ponds Using Geospatial Analysis and Sediment Flow Simulation Modeling in a Nickel Laterite Mine. So these are the topics that I will discuss during my presentation. Excavation, as we all know, can increase the sediment collection in water systems and streams. Possibly that will result to poor water quality. Thus, the need for appropriate silt ponds or catchment areas of the sediment is a must in every surface mine. So our study uses geospatial analysis on identifying suitable areas by generating a suitability map performed in ArcMap and simulates the dynamics of water through 2D and steady flow simulation in HECRAS at Cajano Mining Corporation. It is being used effectively among most environmental planning and analysis. It gives a better view and interpretation of the physical features and the relationship that influences a particular condition in the environment. It is an application that let us compute and visualize a model, 1D and 2D and steady flow. This software can generate a steady varying flow on the channel geometry and river. So our study aims to address the following concerns. Require additional technology development for fast assessment and response time pertaining to runoff mitigation in mine areas. In need of additional quantitative model to compare their existing model in identifying areas where water will most likely accumulate and exits in times of heavy rain, and accessing the area establishments of existing siltation ponds for a possible additional location. For the objectives, we aim to provide data that will identify potential additional areas where water will most likely accumulate and exit during heavy rains. Furthermore, we also aim to provide enough data that will be able to locate additional silt ponds if necessary and to simulate water flow dynamics in order for us to visualize the area where water accumulates and exits during heavy rains and to establish a comparative tool in the actual field scenario by using the generated output of the study. So, our study is situated in Cagdiano, northeastern province of Dinagat Islands with 697,004.81 hectares total area. Its commodities were limonite and saprolite ore, and the area of operation is within the Surigao Mineral Reservation. So these are the process that we did in order for us to come up with our desired output. To start with, we use the HP form distribution, its calculation, and the eigenvector values. So in analytical hierarchy process, it is a tool used to create weights of the layer in performing weighted overlay analysis. Next, we have the data gathering, data extractions, data processing, and reclassifications. For the data gathering, we use the land cover, the DEM or the digital elevation model, road system, soil, geology, rainfall history, which we acquired from the Cajano Mining Corporation. And then the data extraction, its road proximity, slope, and aspect. For the data processing and reclassification, the road system had been projected using projection and transformation in ArcMap data management. After all the maps were converted into raster files, it is then reclassified in order for the data to have the same spatial resolution before performing weighted overlay analysis. So weighted overlay analysis was performed on ArcMap under Spatial Analyst tool. Weights per layer was derived from the AHP result, and weights must be equal to 100% to perform the analysis. So next is the map generation. This is the map generation process. So map generation of each layer was performed and an elevation map with the derived basins. So from the DEM file, we extracted and we come up with the slope and aspect map. And then from the road system, we convert to all maps are converted into raster files, and then we reclassify it and then proceed to weighted overlay analysis. Next is the 2D flow simulation. So in 2D flow simulation, we use the HECRAS or the Hydraulic Engineering Center River Analysis System. So this is the 2D and steady flow simulation flowchart. So first, we import the terrain model and background map layer in RASmapper. So the data that we use is the digital elevation model, which we acquired from the CMC. Then we draw the 2D flow area into the HECRAS geometry using 2D flow area drawing tool. So the 2D flow area was defined to set locations where rain is subjected. We corrected by computing the 2D computational mesh, and we assign the boundary condition, the upstream and downstream. Storage areas are the bases. Then we assign the flow hydrograph using the rainfall datasets, which we also acquired from the CMC. Then the hydrologic data is created. Then we run the unsteady flow analysis, compute, and the unsteady flow simulation model is developed. After the simulation is being developed, we evaluate the existing silt ponds, then we come up with our final output, and then we compare it to the generated data and the actual field scenario. So after all the maps were converted into raster files, we came up with the weighted overlay analysis. Around a total of 166.3141 hectares of CMC tenement, or around 28.88% of the area of the CMC, belongs to moderate to very strong suitability. So the weights we use are the land cover, slope, aspect, soil texture, geology, and road proximity with water delineation. It was suggested by Engineer Ismael from the Cagdiano Mining Corporation to focus on the areas where mining is active because some part of the tenement of the Cagdiano Mining Corporation is still an untouched areas and residential area. So the basins are derived using the DM file or the digital elevation model file provided by the company, and this was done using the hydrology tool under the special analyst tool on ArcMap. So fill was first extracted to get the flow direction and flow accumulation. After deriving the flow direction and flow accumulation, the basins are then identified, and the identified basins are clipped to the areas where mining operation or activities are active. So this is the 2D unsteady flow simulation result. The time variation of the result of the unsteady flow analysis was obtained, the water depth, water velocity, and the water surface elevation. Analysis is subjected to its maximum flow. Its location is dependent upon the cell properties and associated geometry, though the location of maximum value of each result varied over the reach of time. For the dynamics of water flow, the unsteady flow analysis demonstrates how the accumulated areas were found. The analysis depicts how the water behaves as time passes or as the results are obtained. So the rainfall data from January 1, 2020 to December 31 is what we loaded into the flow hydrograph as the boundary condition. So as you can see on the graph, we have 115.60 millimeter as its highest precipitation that occurs on December 27. So for the comparison of generated output in the actual field scenario, we have its differences and similarities. It differs in the usage of HECRAS for simulating the water dynamics, and it differs in software used in deriving the basins. So in similarities, it is similar in the determinants used in finding additional silt ponds, and both practices GIS and environmental analysis. So this is the map of the location of existing silt ponds of the CMC. So Cagdiano Mining Corporation employs 38 silt ponds around its tenement as of March. So the existing silt ponds of CMC are found to be properly located based on the results generated by the study, which shows the true commitment and concern of the company to the environment. So the unsteady flow analysis can simulate storage areas and the hydraulic linkages between storage areas and reveal accumulated regions and the locations of the mine's existing silt ponds, with our proposed additional silt ponds with the legend of color purple. As you can see, we have 5 proposed additional silt ponds. So the proposed silt ponds are based on the generated output from weighted overlay analysis, derived basins, and 2D unsteady flow simulation. So the daily precipitation measured on the rain gauge of the study area used for the simulation and HECRAS is an actual and recent rainfall history data of CMC, which gives the output a more realistic approach to the actual field scenario. So our objectives were achieved, so therefore we concluded that suitability maps derived from weighted overlay analysis provides adequate data to locate suitable areas for silt ponds, considering the parameters used in the study. And we also concluded that the 2D unsteady flow analysis in HECRAS is an appropriate representation of the time series result for the given flow state. It calculates relative flow velocity and direction based on the distance and direction traversed during the simulation. The output of the study and the actual field scenario are both concerned with the mitigating surface runoff, and the study is cost efficient, reduces workforce, and can be performed remotely. Lastly, for the recommendation, number 1, good quality DM file generate more accurate terrain model and maps that is needed on the analysis. Number 2, to use another type of multiple criteria decision making or the MCDM to rank the relative importance of criteria for future studies such as analytical network process, data development analysis, and fuzzy decision making. So number 3, due to the complexity of the Earth's nature, the most precise prediction is impossible, and water behavior can also be incorrect. So it is recommended to explore several approaches such as Bernoulli's principle, St. Flow-Venant's equation, mass conservation, momentum accumulation, and energy conservation are the most extensively used in water modeling. So HECRAS, as presented, may create hydraulic characteristics based on geometric terrain data and observe water surface elevation as a result. So it is recommended as a use in unsteady flow analysis to forecast flood threats and their magnitude and aid in the rapid evacuation during floods. Thank you. Again, my name is Trisharia Bonanza, a 5th-year mining engineering student under the advisory of Engineer Jerome Amper. Thank you.